All right, let me ask you something. Have you ever really thought about the difference between a code and a cipher? I mean, we hear those words thrown around in spy movies all the time, right? But it turns out they're not the same thing at all. They're two completely different ways to keep a secret. So let's dive in and figure out what actually separates them.
For most people, these words basically mean the same thing. We use them interchangeably, kind of like blending and mixing. But in the world of secret messages, oh, they are fundamentally different tools, and they're designed for completely different jobs.
So let's start with codes. The absolute most important thing to remember here is that a code operates on meaning. Yeah, meaning. Think of it less like some secret alphabet and more like a set of secret shortcuts for entire ideas.
What a code does is take a whole meaningful unit, a word, maybe a phrase, even a full sentence, and just swaps it out with a prearranged symbol or word. So for example, instead of telegraphing a big, long, urgent message, you could just send the word accountant. It's all about substituting meaning, mostly for the sake of being efficient.
Okay, so let's break it down. Codes, they need a codebook, which is basically a shared dictionary of meanings. Ciphers, on the other hand, couldn't care less about what the message means. They are purely mechanical. They work on the symbols themselves, the individual letters, using a kind of mathematical recipe, we call it an algorithm, and a shared secret called a key. To really get the difference, let's build our very first cipher together. We're going to use a classic one you've probably heard of, the shift cipher. You might also know it as the Caesar cipher. It's super simple, but it perfectly shows you that mechanical, step-by-step nature of a cipher. All right, here's the recipe. First, we turn our letters into numbers. A is 0, B is 1, you get the idea. Then, we add our secret key. Let's just pick a number, say 19. Now, this mod 26 step, it sounds fancy, but all it means is if we go past 25, which is Z, we just wrap back around to the beginning of the alphabet. And finally, we turn that new number back into a letter. Simple as that. Okay, let's try it out with the letter K. So in our system, K is the number 10. We add our key, 19, and we get 29. Now for that mod 26 step. 29 wraps around the 26-letter alphabet and lands us on 3. And what's the letter at position 3? It's D. We just do that for every single letter, and KASHN becomes the ciphertext .tg. See? So how does our friend on the other end read the message? Well, they just run the process in reverse. They take each letter of our scrambled message, turn it into a number, but this time they subtract our secret key, 19. That mod 26 thing still works to handle the wraparound, and then they convert the final number back to a letter. And here it is, the payoff. Our friend takes DATG, runs the decryption steps with the exact same key, and pop! Out comes our original message, con. As long as you have that secret key, the message is perfectly clear. But what if you don't? This is where things start to get really interesting. See, a good cipher should be secure, even if the enemy gets a copy of your encrypted message. So, how secure is our little shift cipher? Let's find out how to break it. Here it is. This is the cipher's Achilles heel, the number 26. Why? Well, because there are only 26 letters in the English alphabet. There are only 26 possible secret keys you could ever pick. Shifting by 0 is the same as shifting by 26, after all. And this tiny number of possibilities, well, it's a critical flaw. That small number means an attacker doesn't even need to be clever. They can just use brute force. They can just try every single key, one by one. Does shifting by 1 work? No. How about 2? Then 3? With only 26 options, they are guaranteed to find the right key, and it'll probably only take them a few minutes. So yeah, the shift cipher, it turns out it's not secure at all. Now, to get to truly secure encryption, we have to leave the world of letters behind and step into the world of computers. Modern encryption doesn't work on alphabets. It works on binary digits, or bits, those ones and zeros that make up literally all digital information. Let's make this real. We can take something like, say, the specific shade of green in the Khan Academy logo, and we can represent it as a long string of ones and zeros, okay? This is our new message. So, how do we encrypt it? What we need is a mathematical operation that can combine our message bits with a random key. The whole goal is to produce a result that looks like complete random static. We've got 3 main contenders for the job. These logical operators called AND, OR, and XOR. Let's put them to the test and see which one is up to the task.
First up is the AND operator. Now, AND only spits out a 1 if both of the inputs are 1. Otherwise, you get a 0. You see the problem? This means there's a 3 and 4, a 75% chance that the output is going to be a 0. That's a serious bias towards 0. And that is not random at all.
And this bias, it has a very obvious visual effect. When we use AND to encrypt our green color with a random key, the result is this really dark, muddy color. Because AND is biased towards outputting zeros, it just pushes the final color towards black. Not exactly random, is it? All right, next up is the OR operator. It's kind of the opposite of AND. It spits out a 1 if either of the inputs is a 1. And this just creates the opposite problem, a 75% chance that the output will be a 1. Again, this is not that random 50-50 split we desperately need for good encryption. And just like you'd guess, this bias shows up visually. Encrypting our green with OR gives us this super light, washed-out color. Its bias towards 1s just pushes the whole result towards white. So we're still not getting the random noise we're looking for. And finally, we have XOR. It stands for exclusive OR. And this is the magic bullet for encryption. XOR outputs a 1 only when the two inputs are different. So a 0 and a 1 gives you a 1, but two zeros or two 1s, they both give you a 0. The result? A perfect, totally unbiased 50-50 chance of the output being a 0 or a 1. Now that is true randomness. This perfect 50-50 balance is the secret sauce for creating what we call perfect secrecy. It lets us build a truly unbreakable lock. Let's see what happens when we use this on something a little bigger than a single color. So here's an image of the computing pioneer Charles Babbage. Now, if we encrypt this image by combining every single bit with a random key using that biased AND operator, well, you can still pretty clearly make out his face. The original information is just leaking right through. That is definitely not secure.
But now for the magic. When we use the perfectly balanced XOR operator instead, Charles Babbage is gone. Poof. The image has been transformed into pure random static. Every single pixel is completely scrambled. There is absolutely no trace, no pattern, no information from the original image left. Nothing.
And this is where it gets really mind-bending. I mean, think about it. That static image contains zero information. It's just noise. But if you have the exact right key and you XOR it again, boom, the perfect picture of Charles Babbage pops right back out. But here's the crazy part. With a different key, you could get a perfect picture of a cat. Another key, the Mona Lisa. Another key could even reveal a picture of you. Every single possible image is hiding in that static, and they're all equally likely. So without the key, how could you ever know which one is the real message?